Hello, and welcome back to the Sleepy Facts Show, the place where you can drift off gently while learning something new. Tonight, we'll be exploring fascinating facts about Isaac Newton. As you settle in, feel free to let me know in the comments where in the world you're tuning in from. I always enjoy seeing how far these quiet episodes travel. And if you'd like to support the show, you can find those details in the description. But for now, just get comfortable and we'll ease into tonight's topic. Isaac Newton was born on January 4th, 1643, in the small English village of Woolsthorpe in Lincolnshire. England at the time was in the middle of political turmoil that would soon erupt into civil war. Newton's birthplace was a quiet rural farm far removed from the centers of science and learning. Despite these humble beginnings, he would grow up to become one of the most influential scientists in history. Newton was born prematurely and was so small that his mother later claimed he could have fit inside a quart mug. Many people at the time doubted he would survive infancy. Medical care in the 17th century was limited, and premature babies rarely lived long. Yet Newton survived and eventually grew into a healthy child. Newton's father, also named Isaac Newton, died 3 months before his son was born. His father had been a modest but successful farmer. The absence of his father shaped Newton's early childhood and family circumstances. When Newton was 3 years old, his mother remarried a local clergyman named Barnabas Smith. She moved away to live with her new husband, leaving young Isaac behind. Newton was raised instead by his maternal grandmother. This separation reportedly caused emotional strain that Newton remembered even as an adult. As a child, Newton showed an early interest in mechanical devices and construction. He built small machines and toys using wood and household materials. Some of his creations included miniature carts, windmills, and other simple mechanisms. These early experiments hinted at the curiosity that would later drive his scientific work. One of Newton's most famous childhood inventions was a model windmill. According to stories from people who knew him, he built a functioning miniature windmill similar to those used for grinding grain. He reportedly powered the model by placing a mouse inside it to act as a moving force. The mouse even had a small name, the Miller. Newton attended the King's School in Grantham, a nearby town not far from his home village. The school focused heavily on Latin, which was the language used for scholarly writing at the time. Students also learned classical literature and basic mathematics. Newton lived in Grantham during the school term rather than commuting daily. Despite his later brilliance, Newton was not initially viewed as a particularly exceptional student. Early reports suggest he performed only moderately in school. However, he later became more focused on his studies after a rivalry with another student motivated him to work harder. From that point on, his academic performance improved dramatically. Newton's childhood writings reveal that he sometimes struggled with anger and resentment. In one notebook exercise, he listed past sins he believed he had committed. Among them was a statement about threatening to burn down his stepfather's house with his mother inside. Although likely written in youthful frustration, it reveals the emotional tension in his early life. During his teenage years, Newton lodged with an apothecary named William Clark while attending school. Living in the apothecary's home exposed him to chemicals, medicines, and laboratory tools. He observed experiments and preparations related to early medical treatments. This environment may have sparked Newton's later interest in chemistry and alchemy. In 1661, Newton entered Trinity College at the University of Cambridge. At the time, Cambridge was one of England's leading centers of learning. Students there studied a mixture of classical philosophy and emerging scientific ideas. Newton began his university education with modest financial means and worked part-time as a servant to wealthier students. At Cambridge, Newton studied mathematics, philosophy, and astronomy. His coursework included subjects such as geometry, logic, and natural philosophy, which was the early term for science. These subjects formed the intellectual foundation of scientific study in the 17th century. Newton quickly became fascinated with mathematical problems and physical laws. Much of Newton's early education was still based on the teachings of the ancient Greek philosopher Aristotle. For centuries, Aristotle's ideas had dominated European academic thinking. However, by Newton's time, many scholars were beginning to question these traditional views. Newton would eventually help replace them with new scientific explanations. Outside his official studies, Newton began reading more modern scientific works on his own. He studied writings by Galileo Galilei, René Descartes, and Johannes Kepler. These thinkers challenged traditional views about motion, astronomy, and mathematics. Their ideas strongly influenced Newton's developing scientific perspective. In 1665, the Great Plague struck London and spread across much of England. Universities, including Cambridge, closed to prevent the disease from spreading among students. Like many others, Newton returned to his family home in Woolsthorpe. This unexpected break from formal study gave him time to think and experiment independently. Newton remained at Woolsthorpe for roughly 2 years while the plague continued. During this time, he worked alone, away from professors and classmates. The quiet rural setting allowed him to concentrate deeply on scientific questions. Many historians believe this period was the most productive time of his life. While living at home during the plague years, Newton developed several groundbreaking ideas. He began exploring the mathematics that would later become calculus. He also experimented with light and optics using prisms. These discoveries laid the groundwork for many of his later achievements. Because of the remarkable progress Newton made during this period, it is often called his Annus Mirabilis, meaning Year of Wonders. The phrase reflects the extraordinary number of ideas he produced in a short time. In just a few years, Newton developed insights that would change science forever. Few scientists have experienced such a productive burst of creativity. One of the most important ideas Newton began developing during this time was calculus. Calculus is a branch of mathematics used to describe change and motion. It allows scientists to calculate how quantities vary over time. Newton created these mathematical tools to help solve problems in physics and astronomy. During the same period, Newton also began thinking seriously about gravity and motion. He wondered why objects fall toward the Earth and how the same force might affect the moon and planets. These questions led him toward the concept of universal gravitation. This idea would later become one of the cornerstones of modern physics. Isaac Newton formulated what are now known as the 3 laws of motion. These laws describe how objects move and how forces affect that movement. Before Newton, motion was poorly understood and often explained using outdated philosophical ideas. His laws provided a clear mathematical framework that scientists still use today. Newton's laws of motion became the foundation of classical mechanics. Classical mechanics is the branch of physics that explains how objects move under the influence of forces. For centuries, engineers and scientists relied on these laws to design machines, buildings, and vehicles. Even today, they accurately describe most everyday motion on Earth. Newton's first law of motion is often called the law of inertia. It states that an object at rest will remain at rest, and an object in motion will continue moving in a straight line unless acted on by an external force. This concept explains why a rolling ball eventually stops due to friction. Without outside forces, motion would continue indefinitely. The second law of motion describes how force, mass, and acceleration are related. It is often summarized by the equation F equals ma, meaning force equals mass times acceleration. This law explains how stronger pushes or pulls cause objects to speed up or change direction. It also shows why heavier objects require more force to move. Newton's third law of motion states that every action has an equal and opposite reaction. This means that forces always occur in pairs. For example, when you push against a wall, the wall pushes back with equal force. This principle explains many everyday phenomena, including how rockets launch into space. Newton also developed the law of universal gravitation. This law describes how every object with mass attracts every other object with mass. The strength of the attraction depends on the masses of the objects and the distance between them. Newton showed that gravity is a universal force acting throughout the universe. According to Newton's theory, gravity pulls objects toward each other across vast distances. This same force that causes an apple to fall to the ground also keeps the moon in orbit around Earth. Newton realized that the laws governing objects on Earth could also apply to celestial bodies. This was a revolutionary idea at the time. The famous story about Newton discovering gravity involves a falling apple. According to legend, Newton saw an apple fall from a tree and began wondering why objects fall straight downward. While the story is often simplified, it reflects his curiosity about gravity. The event helped inspire his thinking about how gravitational forces work. Newton himself mentioned the apple story later in life when discussing his ideas. He explained that seeing an apple fall made him question why the moon does not fall to Earth in the same way. This led him to think about gravity acting over large distances. The story became one of the most famous anecdotes in scientific history. Newton demonstrated that gravity affects objects both on Earth and in space. Before his work, many people believed that the heavens followed different rules than the Earth. Newton showed that the same natural laws apply everywhere in the universe. This idea helped unite physics and astronomy into a single scientific system. Newton performed many experiments using prisms to study light. By passing sunlight through a glass prism, he could separate it into different colors. This allowed him to study how light behaves when it bends or refracts. His experiments helped reveal the true nature of light. Through these experiments, Newton discovered that white light is actually a mixture of many different colors. When light passes through a prism, the colors spread out into a spectrum. This spectrum includes red, orange, yellow, green, blue, indigo, and violet. Newton realized that these colors were already present in white light. Newton demonstrated that the prism itself did not create the colors. Instead, the prism simply separated the different wavelengths of light. He proved this by passing the colored light through another prism to to recombine it back into white light. This experiment helped confirm his theory about the nature of color. From these observations, Newton concluded that color is an inherent property of light itself. This contradicted earlier beliefs that color came from changes in the medium through which light traveled. Newton's work showed that different colors correspond to different types of light. This discovery was a major breakthrough in optics. Newton famously described 7 colors in the visible spectrum. Some historians believe he chose 7 partly for philosophical reasons because the number 7 had symbolic importance at the time. Regardless, his description helped establish the modern concept of the color spectrum. Newton proposed that light was made of tiny particles. He called this the corpuscular theory of light. According to this idea, light traveled in straight lines because it consisted of small particles moving through space. This theory helped explain some optical phenomena. The corpuscular theory remained influential for many years. However, later scientists such as Thomas Young and Augustin Fresnel suggested that light behaved more like a wave. Eventually, both ideas were partly confirmed through modern physics. Today, we understand that light has both particle and wave properties. The debate over the nature of light continued for centuries after Newton's work. Scientists conducted experiments to determine whether light behaved more like particles or waves. Newton's authority was so respected that his particle theory dominated earlier discussions. Only later experiments shifted scientific opinion toward wave theories. In 1704, Newton published a book titled Optics. Unlike his earlier mathematical works, this book described his experiments in a more accessible style. It explained how light interacts with prisms, lenses, and other materials. The book became one of the most influential books in the study of optics. Optics also included discussions of reflection, refraction, and color. Newton described many detailed experiments that readers could repeat themselves. The book influenced generations of scientists studying light and vision. Even centuries later, many of Newton's observations remain accurate. Isaac Newton independently invented calculus, one of the most important branches of mathematics. Today, it remains one of the core mathematical tools used in science. Around the same time Newton was developing calculus, the German mathematician Gottfried Wilhelm Leibniz was working on similar ideas. Leibniz developed his own form of calculus independently. His notation for calculus eventually became the standard used today. This simultaneous discovery later led to controversy. A major dispute arose between supporters of Newton and supporters of Leibniz over who invented calculus first. Both sides accused the other of plagiarism. The disagreement became one of the most famous scientific controversies in history. It divided European mathematicians for decades. Newton used calculus as a powerful tool for solving problems involving motion and gravity. It allowed him to calculate how objects accelerate and how forces act over time. These calculations were essential for understanding planetary motion. Without calculus, many of Newton's discoveries would have been impossible. Newton referred to his version of calculus as the method of fluxions. In his system, quantities that change over time were called fluents, and their rates of change were called fluxions. This terminology was unique to Newton's mathematical approach. However, it was eventually replaced by Leibniz's notation. Calculus quickly became essential for scientific and engineering work. It allows mathematicians to describe curves, motion, and rates of change with precision. Scientists use calculus to predict planetary orbits, calculate speeds, and design complex machines. Newton's early work helped establish the foundations of this powerful mathematical system. Newton was famously reluctant to publish many of his discoveries. He often kept his ideas private for years before sharing them with others. This secrecy sometimes caused confusion about who discovered certain concepts first. In the case of calculus, it allowed others to publish similar work sooner. In 1687, Newton published his most famous scientific work, Philosophiae Naturalis Principia Mathematica. The title translates to Mathematical Principles of Natural Philosophy. The book presented his laws of motion and theory of gravity. It is widely considered one of the greatest scientific works ever written. The book is commonly referred to simply as the Principia. It used advanced mathematics to explain the motion of objects on Earth and in space. The work was extremely complex and difficult to read. Even many scientists struggled to fully understand it at the time. The Principia revolutionized the way people understood the universe. It showed that natural events followed predictable mathematical laws. This idea helped establish modern scientific thinking. The book remained the foundation of physics for more than 2 centuries. Within the Principia, Newton carefully explained his 3 laws of motion. He also described how gravity operates between objects. Using these laws, he was able to explain the movement of planets, moons, and comets. His work unified terrestrial and celestial mechanics. The astronomer Edmund Halley played a crucial role in the publication of the Principia. Halley encouraged Newton to organize and publish his discoveries. When the Royal Society could not afford the printing costs, Halley paid for the publication himself. Without his support, the book might never have appeared. Halley's encouragement helped bring Newton's ideas to the wider scientific community. He recognized the importance of Newton's work immediately. Halley's efforts ensured that Newton's discoveries would influence future generations. Today, Halley is remembered not only for Halley's comet, but also for supporting Newton. The Principia provided a mathematical explanation for planetary motion. Before Newton, astronomers knew the planets followed certain patterns, but did not fully understand why. Newton showed that gravity could explain these movements. His theory revealed that planets move in predictable orbits due to gravitational attraction. Newton demonstrated that Johannes Kepler's laws of planetary motion could be derived from gravity and motion. Kepler had described how planets moved, but he did not know the physical cause. Newton's work explained the underlying force responsible for these motions. This connection strengthened the scientific understanding of the solar system. The Principia relied heavily on advanced geometry and mathematical reasoning. Newton used detailed calculations to support his theories. His arguments were precise, but often difficult for readers to follow. For more than 200 years, Newton's ideas in the Principia shaped scientific thought. His laws successfully explained the motion of planets, falling objects, and many other phenomena. Scientists used his theories to predict new discoveries in astronomy and physics. Only in the early 20th century did Einstein's theories begin to modify Newton's understanding of gravity. Isaac Newton invented the reflecting telescope in the late 1660s. Earlier telescopes used lenses to gather and focus light. However, lenses often created distortions that blurred images of distant objects. Newton's design used mirrors instead, which greatly improved image clarity. Reflecting telescopes use a curved mirror to collect and focus light. This mirror reflects the light to a smaller mirror that directs it to the viewer's eye. The design avoids many problems caused by glass lenses. One major advantage of Newton's telescope was that it eliminated a problem called chromatic aberration. This distortion occurs when lenses bend different colors of light by different amounts. The result is a blurred or rainbow-colored image. Mirrors reflect all wavelengths of light equally, avoiding this issue. Newton built the first working model of his reflecting telescope around 1668. The telescope was relatively small, but demonstrated the effectiveness of his design. This innovation marked a major improvement in astronomical instruments. Newton presented his telescope to the Royal Society of London in 1671. The instrument impressed the scientists who examined it. They recognized the potential of the new design for astronomical research. As a result, Newton quickly gained attention within the scientific community. The reflecting telescope design Newton created remains widely used today. Modern observatories often rely on large reflecting telescopes to study distant galaxies and stars. These telescopes use the same basic principles Newton introduced. His invention helped shape the future of astronomy. Newton spent considerable time experimenting with lenses and mirrors. He carefully polished and shaped optical components for his instruments. These experiments allowed him to better understand how light behaves. His hands-on approach combined theory with practical craftsmanship. He often worked alone in his laboratory, performing careful experiments. His meticulous methods helped produce reliable results. Newton eventually became the Lucasian Professor of Mathematics at Cambridge University. This prestigious position had previously been held by notable scholars. The professorship was dedicated to advancing the study of mathematics and science. Newton held the Lucasian Professorship for nearly 30 years. During this time, he continued developing many of his scientific ideas. He also taught students and contributed to academic life at Cambridge. The position provided him with both financial support and intellectual freedom. In 1672, Newton was elected a Fellow of the Royal Society. The Royal Society was one of the most important scientific organizations in England. Its members included many leading thinkers of the scientific revolution. Election to the society was a significant honor. Newton later became president of the Royal Society in 1703. This leadership role gave him considerable influence over scientific research in Britain. He presided over meetings and helped guide the society's activities. Newton remained president until the end of his life. As president of the Royal Society, Newton oversaw many scientific discussions and publications. The society played an important role in spreading new scientific ideas. It allowed researchers to share experiments and discoveries with one another. Newton's leadership helped strengthen its influence. Newton was knighted by Queen Anne in 1705. This honor made him Sir Isaac Newton. Although he was already famous for his scientific work, the knighthood recognized his contributions to the nation. It was unusual at the time for a scientist to receive such recognition. The knighthood elevated Newton's social status within English society. He was now considered part of the country's respected elite. This recognition reflected the growing importance of science in public life. Newton's achievements had made him a national figure. Later in his career, Newton accepted a position as Warden of the Royal Mint. The Royal Mint was responsible for producing England's coinage. The position initially involved overseeing the quality and security of the currency. Newton approached the job with surprising seriousness. Newton was eventually promoted to Master of the Royal Mint. This role gave him full authority over England's coin production. He supervised the redesign of coins and the improvement of minting processes. The position also brought him considerable wealth and influence. During his time at the Royal Mint, Newton helped reform England's currency system. He worked to combat counterfeiting, which was a major problem at the time. Newton personally investigated counterfeiters and gathered evidence against them. His efforts helped stabilize the country's money supply. Isaac Newton was known to be an extremely private and secretive person. He often avoided sharing his ideas until he was absolutely certain of them. Even close colleagues sometimes found it difficult to understand what he was working on. This tendency towards secrecy occasionally slowed the spread of his discoveries. Newton frequently delayed publishing his scientific work. He worried about criticism and preferred to perfect his ideas before presenting them publicly. As a result, some of his discoveries remained hidden in notebooks for years. This habit sometimes caused confusion about when certain ideas were first developed. In addition to physics and mathematics, Newton spent many years studying alchemy. Alchemy was an early form of chemistry mixed with philosophical and mystical ideas. Alchemists believed that substances could be transformed into others, such as turning base metals into gold. Newton conducted numerous experiments in search of hidden properties of matter. Newton wrote thousands of pages about alchemical theories and experiments. Much of his work remained unpublished during his lifetime. He believed that ancient scholars had discovered secret knowledge about nature that could still be uncovered. Today, historians view his alchemical studies as part of the broader scientific curiosity of his era. Newton was also deeply interested in theology and religious history. He spent many years studying the Bible and writing detailed religious analyses. In fact, he wrote more about theology than he did about physics. These writings explored topics such as prophecy, church history, and biblical interpretation. Some of Newton's religious views differed from the official beliefs of the Church of England. He privately rejected certain traditional doctrines, including the concept of the Trinity. Because such views were controversial at the time, he kept them largely secret. Revealing them openly could have damaged his career. Newton never married and had no children. Much of his life was devoted to study and research rather than family life. He often worked long hours alone, focusing intensely on scientific problems. This solitary lifestyle may have contributed to his remarkable productivity. Newton sometimes became so absorbed in his work that he forgot to eat or sleep. Stories from acquaintances describe him losing track of time while studying. On occasion, he would leave meals untouched while thinking about a mathematical problem. His intense focus became one of his defining personal traits. Newton filled numerous notebooks with observations, calculations, and experimental ideas. These notebooks contain thousands of handwritten pages. Many of them were only discovered or carefully studied centuries later. They reveal the extraordinary depth and range of Newton's curiosity. Isaac Newton died on March 31st, 1727, in London. Newton died at the age of 84. This was considered an advanced age during his lifetime. In his later years, he suffered from various health issues, including digestive problems. Despite this, he remained intellectually active until near the end of his life. Newton was buried in Westminster Abbey in London. This historic church is the resting place of many important British figures. Being buried there was a great honor rarely granted to scientists. Newton's burial recognized the enormous impact of his work. Few scientists had received such public recognition before Newton. His funeral was attended by many prominent members of British society. Political leaders, scholars, and nobles all paid their respects. Newton's work shaped the development of physics for centuries. His laws of motion and gravity explained a vast range of natural phenomena. Engineers, astronomers, and mathematicians all relied on his theories. For generations, Newton's ideas formed the foundation of scientific education. In the early 20th century, Albert Einstein introduced new theories that modified Newton's understanding of gravity. Einstein's theory of relativity showed that gravity could be explained through the curvature of space and time. Even so, Newton's laws still provide accurate predictions in many everyday situations. Scientists continue to use them for practical calculations. Newton's laws remain highly useful for describing motion on Earth. Engineers use them to design vehicles, buildings, and machinery. They are also essential in fields such as aerospace engineering and mechanical design. For most ordinary conditions, Newton's equations work extremely well. Newton's discoveries played a major role in the scientific revolution. This period marked a dramatic shift in how people understood the natural world. Instead of relying on tradition or authority, scientists increasingly used observation and mathematics. Newton's work helped demonstrate the power of this new approach. Because of his extraordinary contributions, Newton is widely regarded as one of the greatest scientists in history. His ideas transformed physics, mathematics, and astronomy. Few individuals have influenced science so profoundly. Even centuries later, his work continues to shape modern knowledge. Isaac Newton fundamentally changed humanity's understanding of the universe. He showed that natural events follow consistent laws that can be described mathematically. These insights allowed scientists to predict the motion of planets, falling objects, and many other phenomena. In many ways, Newton helped reveal the underlying order of the cosmos. That brings us to the end of tonight's episode. If you'd like to hear more calm explanations like this, you can follow or subscribe wherever you're listening. And a quiet thank you to the supporters who help make this show possible. If you'd like to support the show as well, you can join them through the Patreon link in the description. Until next time, sleep well.